So what I like to do in this first part of the talk is to first put in context why polycrystalline graphene and two-dimensional materials are now becoming mainstream for a variety of applications. And this is really stunning, actually. The second part of the tutorial, which is, let's say, the core of the tutorial, is actually to discuss the correlation between the morphology of those polycrystalline materials and their basic electronic and transport properties. And you will see that actually what we have as a kind of main potential detrimental characteristics, the grain boundaries, could, in some cases, become an added value. And if we are good in time, I will also go to more exotic aspects of transport, spin transport, or transport under high magnetic field in those polycrystalline graphene, and we show some kind of very funny property. So last week we had the chance to listen to Rod Wolf, who together with Luigi Colombo and Zhe Song Li pioneered the large scale growth of polycrystalline graphene, just like in 2009. And their work actually really stimulate a huge impact, a huge amount of activities all over the world, in the East, in Korea, in China, in Japan, and in Europe, in the United States. So they have really started the field. And in their paper, they basically put on scene the main ingredients of what the technology should look at, which is not only to grow the material, but also to transfer the materials to relevant substrate for a given type of application. And also to characterize these materials as much as possible to really get, without any doubt, the fine detail about what you are growing. I say, Peter, you have decided to put a lot of efforts in networking European groups involved in the graphene research. And this graphene flagship was launched in 2013 with a substantial funding in order to address the potential, to explore the potential of this graphene and related layered materials for a broad scope of application, and try to bring it to reality in terms of to bring it to lab to fab, if I may say. Actually, at the kickoff meeting in Brussels, here you see our graphene flagship director, Jari Kinnared, which is holding in his hand a very large graphene scale material, which was produced by Istron, a tool manufacturer involved in the consortium. So that's from start, that was one of the main targets, to bring these materials to upscale these materials to be applicable in a commercial application. Few months ago, actually, the European Commission, together with the graphene flagship, they launched the so-called experimental pilot line. So which is really the ultimate step to upscale production of electronic devices and really to develop all the process for manufacturing and scaling up for a really targeted market application. So within this consortium, you have companies such as Graphenea, which is a Spanish company, and which is actually offering already graphene foundry services to customer on wafer and with customized design. So really the revolution is really ongoing now. It's really ongoing. And actually this CVD grown graphene is really a material that is essential for most of the high-tech application that we are envisioning, especially in our graphene flagship. Here you have a list. I want just to point out very recent result, actually published just like days or week ago. And that's unbelievable. All the things now is really blossoming and going really high in TRL and coming very close to commercial products, already entering into commercial products. This is an example of integration of photonic devices. You know that the data traffic is exploding now with the cloud and data centers, and we need really to have ultra fast operation, ultra broadband photodetectors and modulators. And these are two papers published by a consortium between CNIT and IIT in Italy and Cambridge, where they have demonstrated not only that this the material is really outperforming in terms of single device, but that you can mass produce devices for real application. This is another really beautiful example of graphene-based, CVD graphene-based brain implants, which can really probe neural activity in an unprecedented manner. And now at the moment, there is a spin-off of this activity piloted by Jose Garrido in my institute, which is really working with other companies, and they already have a commercial market on the a commercial product on the market now. So finally, I found this breakthrough I think I put it just this morning in my presentation, which is also the large-scale integration, wafer-scale integration of two-dimensional material-based heterostructures, which is also essential for certain type of applications. So co-integrating graphene with boron nitride and transition metal chalcogenide, for instance. So this consortium has already demonstrated that this is possible and compatible with what we call the back end of the line integration for integrated circuits. So if you think about this, the phone for the smartphone of the future, you might see actually that this two-dimensional material might become really invasive material in this technology. And we know if CVD graphene will even ever allow to bring this science fiction communication tool surfacing to reality. So that's really a beautiful revolution. But let's come now to the very concrete aspect of the materials. So this cartoon is what we would like to have. It's a growth of a single crystal, but what we are facing with is a different reality. We are facing with a material which is polycrystalline. You have grain with different orientation, and you have a lot of these grain boundaries which separate different grains, which are source of worries. So let's enter now into the core of the presentation. These grain boundaries are part of the problem that might impede the good electronic transport, for instance. But there are also additional sources of contamination when you will detach your graphene or 2D material from the metallic substrate and transfer it to an oxide substrate, for instance. So you have to develop these processes as less invasive as possible, and you have to deal with that. But grain boundary is really one of the central questions. Or do you need to have really a single grain for a target application, or can you deal with a polycrystalline graphene with a much smaller grain size? So that's really an open question. And Zhongfang Liu from China actually point out that one of the probably key issue for industrial manufacturing is the fact that you wanted to avoid high growth temperature and long growth time for efficiency of the production. So there are a lot of activity which are trying to minimize the growth time and minimize the temperature. So this is an example of the group of Zhongfang Liu at the Beijing Graphene Institute, where he developed a different type of process using ethane, and he could demonstrate that he could reduce the temperature down to 700 degrees C compared to the state of the art. And he was able to really improve quite substantially the growth rate with these methods compared to other state-of-the-art growth method. So certainly this slide has to be updated, and there will be, the objective we have is to go for fast growth rate and very large element size, of course, but that's not that easy. And we need standardization. We need to characterize the material. So really, the question of the basic morphology of the polycrystalline graphene, all this impact on the properties is really a major question. 2014, actually, Samsung and collaborators, SKKU, also developed their own methods and implement this graphene and replace ITO in mobile phone. what they ask in the paper, they try to find a connection between the morphology of the material. So they study different type of polycrystalline graphene with average grain size, which were different. And they try to make a correlation with the sheet resistant. At that time, the correlation was not very convincing, but the question was there. What is really the optimized polycrystalline graphene that we need for a given application? So this polycrystalline graphene have an essential characteristic is that you have these grains which are arranged in a different fashion, and they have different average grain size. But most importantly, you at the boundaries of this grain with different orientation, you have a reconstruction of the bonding, which end up with this type of structural defects. And they are non-hexagonal member ring like heptagon, pentagon, octagon, and so on and so forth. In most cases, you have an irregular sequence of this type of defect, and it appears that from time to time, occasionally, you may find some grain boundary that looks like periodic, some kind of repetitive, but this is really not the most often topic. So you can study these from the simulation point of view. You can develop some molecular dynamic approach, and you can create this structure with an increasing average grain size. For instance, you can try to see how these grain boundaries are sensitive to chemical functionalization, to cracking, and so on and so forth. What is really nice is actually the percentage of non-hexagonal ring in these models is actually very, very close to the experimental observation. So we have something which is quite realistic in that regard. In addition, we know that the simulation demonstrate that you have a lot of strain and deformation fields at the grain boundary side. So you have to take into account the fact that you have this natural rippling of the system which take place, and the interaction with the surface will make the situation even more complicated. So those grain boundary, basically what they produce is they create boundary states. So this is a beautiful picture which was given to me by one of my close friends that sadly passed away last year. And this is really the picture I love, where you see really the increase of the electronic density at the grain boundary. And this is something, of course, that you can explore through simulation and see if there is any type of doping or this electronic density actually size depending on the condition. So this technique of scanning tunneling spectroscopy is very useful. It has been used in the past for investigating the fingerprint of defects, such as these structural defects, stoneways, or dye vacancies. But what is really interesting now is that we see we have a value of these boundary states. So let me first introduce this work again from Zhongfang Liu, in which they study a polycrystalline boron nitride. And here you see the local density of states, they measure experimentally across along two different grain boundary, one which is very bizarre with a kind of 4-8 member rings, another one which is more conventional with heptagon and pentagon. And if you look at the local density of state, which is related to this derivative of the current versus voltage, and you compare with the usual gap of boron nitride, you see that you have the formation of state inside the gap and impurity state that can be formed, and that will be very dependent on the type of grain boundary that you are studying actually. In this case, I'm showing the interesting situation where you have an in-plane hybrid between boron nitride and graphene. So you have a very different transition between a strongly insulating material and a semi-metal. And this can be actually grown quite easily. And here you see the simulation, what's going on at the boundaries. This is the local density of states along the boundaries between graphene and HB. And then you see a lot of those impurity states, but quite spectacularly, I will say, it turns out that we can use these impurity states as an emitter. So it was demonstrated just like last year that these boundary states actually will create blue emission in the blue. So here you see a circular graphene disc immersed into a boron nitride, and then you look at the fluorescence of the system, and you have the emission in the blue. So that's really nice. That's a characteristic, more than a characteristic. That's a potential property of these boundary states. So now, how can we characterize a polycrystalline graphene and all these grain boundary networks in quite details? One of the methods that was developed by IGFO, by Vosner and Frank Coppens, was to use a near-field photocurrent nanoscopy. This is a kind of very nice approach, and here you see the picture of this polycrystalline graphene, and particularly you see an alternance between red and blue zone, which are related to the sign of the photocurrent. It turns out that the photocurrent is connected with the so-called Seebeck coefficient. So the photocurrent is governed by thermoelectric effect in this experiment. And so one important quantity is the Seebeck coefficient that tends to be strongly impacted by the grain boundary, but it's almost independent of the grain size. So this impact of the grain boundary is actually reflecting the photocurrent, and here you see a simulation of this photocurrent compared to the experimental data. So that's a kind of nice characterization, which is really local scale. Another very interesting work by the groups of Wensai Ren and Yumin Sheng is to investigate the thermal property of polycrystalline graphene by varying the grain size. So they introduce a very tricky, a very nice growth sequence in which they start with a conventional, let's say, regular polycrystalline graphene, and then by some treatment with argon and hydrogen, they could really tune the average grain size down to nanometer scale. So this is really spectacular. I think that this is almost the only work I know in which they could go to a few nanometer average grain size. And here you see some example about how by changing the temperature they will increase the grain size. And most importantly, you see the thermal conductivity that is measured as a function of average grain size, and they can extract a scaling law. So there is really the effect of the grain boundaries in action, and you can see how it scales with increasing the grain size. So this actually can be well connected, well matched with simulation. So it's kind of very under control. Another central information that we want is all the electric transport properties scale with the average grain size. And this is again a measurement by the same people in which they measure the sheet resistance as a function of average grain size. And you see that when you increase the grain size, you have almost initially a linear decay of the sheet resistance. Okay, so that's a very interesting scaling law to know. Here I show some pictures, some movie that I show it because it is a movie which, sorry, I have to go here. I have to, so this is an electron inject in the center of a grain boundary, and then you look at all these wave packet actually move along this polycrystalline graphene, and you see that the situation is kind of complex because you have some type of confinement of the wave packet inside the initial grain, whether you have also some part which move away. So it's not so easy to estimate the transport length scale in such a complicated material. And actually, as Peter said, you have to recourse to efficient numerical simulation of quantum transport in order to access this type of quantities. So this is what we have been developing during many years. And actually, these methods has a surprising supremacy in the sense that we can simulate the charge mobility, for instance, of a polycrystalline graphene in a couple of weeks, and it will take us like a billion years if we would use a kind of alternative algorithm. So it really gives us some very large capability. And as a result, for instance, we show what we get several years ago. It is a elastic mean-free path as a function of energy for different polycrystalline graphene with an increasing average grain size. And what you see is that as you increase the grain size, you increase the mean free path. But what we found out is that was really a linear scaling. It was really linear with the grain size. So it looks like almost obvious, but here you come with the quantitative, the factor that pilots the mean free path. And if we simulate the mobility also as a function of the grain size and the charge density, we could connect and compare with the experiment result. Here is an example where you have a graphene, CVD graphene on boron nitride, and you get the typical large increase of the mobility when you go to very low density. Actually, from the simulation, we could predict that if the polycrystalline graphene is very clean somehow, just the impact on the transport is just due to the grain boundary. Typically, for a grain boundary, average grain size of 1 micron and the charge density of 310 to the 11, which is the usual value that are used, you will get a mobility of 300,000. So this is giving a kind of number between your morphology, the morphology of the polycrystalline graphene, and the eventual charge mobility that you will obtain. Okay, but let's go a bit into the quantitative comparison. And to do that, we have to I'm commenting here this experiment, which are very interesting, in which you measure the resistance inside grains and then across the grain boundary. So by doing that, you can really get an information about the impact of the grain boundary. So you can extract the so-called grain boundary resistivity, which really is a fingerprint above the grain boundary on electronic transport. It turns out there have been many groups, experimental groups, that did this type of experiment, and they end up with a value of the grain boundary resistivity, which scale within this interval. So 0.5 to 10, let's say, kilo micron, which is very weakly temperature dependent. And when compared with a very clean polycrystalline graphene, actually, it's just like 1 or 2 order of magnitude higher. So the question was, what could be the explanation? So there are many possible additional sources, but as observed by Professor Yongli Li from SKKU in 2012, when you have graphene on top of your metallic substrate, actually there is oxidation of your metallic substrate, which takes place underneath the grain boundary. So this was a way to image the grain boundaries, and actually it is related to the fact that those grain boundaries are much more chemically reactive. So the adsorbent, the chemical adsorbent, will actually be stick there and will also cross through and oxidize the metal. So we know from the simulation that these grain boundary are more chemically reactive. So we have to take this into account in the simulation. That's what we did in our work, and we wanted to look at all, for instance, the sheet resistance with scale when you increase, the contamination, let's say, of this grain boundary. And again, I'm showing some picture of my friend, which found really this kind of chemical functionalization of grain boundary by hydrogen in his laboratory. So here is a result of the simulation of the sheet resistance versus the average grain size. We also have put some experimental data, and we find again this downscaling, linear downscaling of the sheet resistance. But of course, if you increase the contamination, here we show the case with hydrogen, then you will increase the resistance. So eventually, you can match the range where experiments estimates are located. And it turns out this work I just mentioned before by the group of Wen-Sai Ren and Wiming Cheng, they have basically for the same value, we enter into the same interval, and we could say, okay, that will correspond to grain boundary contaminated by, let's say, half or half of the grain size boundary would be contaminated. So we have some kind of guidance by comparing simulation and experimental data. An important remark is actually, if you want to use polycrystalline graphene for flexible electronic, what you will need is typically this 0.0 kilo ohm and you see that you can achieve that by grain size which are no more than a few microns, up to 10 microns. So it really showed that in the experiment we have additional source of contamination, because usually the sheet resistance remains larger than 10 kilo. So this is a grain boundary resistivity, which I say it's a good factor or figure of merit for the grain boundary. And this is a simulation of or sample by changing the degree of contamination. And these are some other data report from the literature. So mostly those grain boundary are more resistive to some extent. So this is not only the contamination per se, but you see that here you have an experiment that actually much better. And this is a case where people use really ultra high vacuum and low temperature, and they look by this 4-point STM probe. They could really go and measure the grain boundary resistivity in a very controlled fashion, free from contamination. So the matching is quite remarkable. But you can go beyond that, and you could say, okay, but if grain boundary are sensitive to chemicals, maybe there will be a difference and maybe a way to sense somehow a different type of chemicals. And here is a simple simulation where you see how the grain boundary resistivity is upscaling by increasing the percentage of absorbate, either hydrogen or hydroxyl. And you really see visually that there is a big difference, which actually is related to what kind of impurity states are created under the chemical interaction with this adsorbent. So you may have either localized states or states which form more impurity bonds. And this was an important study by Garrido, who tried to look a bit deeper into that and try to compare polycrystalline graphene-based device, either under some weak oxidation by using an ozone treatment or by hydrogenation. And here you see, so he could monitor the degree of oxidation of hydrogenation by optical measurements. But then they looked at the device characteristics, and they found a very big differences. In the case of oxygen, actually these are very different. Those are different devices. You see that you have some kind of, initially a kind of smooth decrease of the mobility by the increasing the density of this oxygen, but at some point there seems to be a breaking point, and the drop in mobility is large. Whether there was no dispersion in the device for hydrogen, and they all collapse into the single curve with a much smoother decay versus density. And what we gain as information from this study is a very interesting aspect of what all grain boundary actually respond to chemical functionalization. It turns out that when you have oxygen, the oxygen introduce a lot of strain because they create mainly epoxide defect. And what happened when we get this sudden drop of the mobility is basically because we have completely functionalized the grain boundary state, and then the strain is just cracking those grain boundaries. So these cracks are seen in the experiment, and they are correlated to the sudden drop of the mobility of the device. And differently in the case of hydrogen, this transition was not seen, and from the experiment and also from the simulation side. So that's a very interesting features of the grain boundary, their reactivity to chemical functionalization. Some people have used actually the grain boundary as a factor to probe, to detect some molecules. So here you see there was a publication in HOCOM, but also a patent where they measure the sensitivity of their device to gas exposure. So this sensitivity is changed the resistance. And here you see that if they have an isolated grain boundary, when you have this dimethyl methyl phosphonate under action, you have a huge increase of the sensibility. So they have really detected these molecules coming through this grain boundary. And actually, this graph is also interesting because you see that the sensitivity, which was gigantic initially, will drop by increasing the number of grain boundary. This is shown actually in this in this device, but still, at the end of the day, you still keep a decent sensitivity of 20%. And this is really only due to the nature of grain boundary and the fact that they can probe some chemical interaction, and you can have an electrical readout. Finally, I'm showing this paper, which also is a kind of fascinating paper, where using a CBD graphene-based field effect transistor, it was possible to monitor the neuronal activity. So neurons were fabricated or not fabricated. They were somehow they were grown onto the device, and then under proper liquid condition, it was possible to measure the electrical response. And it turns out that it was demonstrated. I mean, there was demonstrated. The interpretation of the data was actually really strongly suggesting that grain boundary were providing some kind of pathway for the ion channel, which are activated during neuron activity. So this is really really nice, and the role of grain boundary here was essential to understand the experimental data. So I recommend interesting people to look at the paper, because there are some kind of quite a lot of details to come to that conclusion. So I think, I'm doing, Peter, with the time. The chairman, I think I should have some free time. Okay, let me.
You have around 9 minutes.
Wow. Okay, so I think I'm doing well. So some additional result I would like to show. One is related to this quantum Hall effect. I mean, quantum Hall effect in graphene has been one of the major breakthrough because graphene exhibit a completely anomalous quantum Hall effect, and especially at this is a zero energy Landau level, which is found in the material where you have the coexistence of electron and hole, give rise to the so-called half integer quantum Hall effect. So the sequence of plateau is very different to what you find in the conventional metallic conducting two-dimensional system. So what will happen with, and this has been observed in a clean graphene, an exfoliate, mechanically exfoliate graphene layer. So what happens if you have polycrystalline graphene? Actually, it turns out that these grain boundary are impeding the formation of Landau level. You will see an illustration of that. What we plot here is a sequence of all the density of states is changing by increasing the magnetic field. So since our grain boundary are quite small, we go to very, very large magnetic field, okay? And you have in the inset the corresponding Landau level structure for completely clean graphene sample. So you see that, you need to go to extremely large magnetic field in order to get the signature of this zero energy Landau level, and you start to have the other one. Basically, what is important is that your magnetic length, which is a characteristic length scale for the Landau level, becomes smaller than the average grain size. Because what you will see here is actually when we project the density of state exactly at the center of this emerging Landau level, as we think, what we see that the projection of the states is mainly on the grain boundary, and it's very difficult to form inside the grain. Eventually, you can form your Landau level. The contribution of the Landau level becomes non-zero inside the grain once the magnetic length is short enough, so the magnetic field is strong enough. So one question, of course, would be that if your magnetic states are strongly confined in the grain and the grain boundaries are acting like a barrier, what will happen in terms of transport mechanism? So it's likely that you have a more open conduction between grain, and so far on the experimental side there have been some attempts, but there was no the very small grain polycrystalline graphene that have been grown recently by Wen-Sai-Ren and collaborator were not available to make such kind of measurements. Actually, it goes a step forward. If you measure the transport in such a polycrystalline graphene, you will have something which is quite unusual, because as I said, at the center of this Landau level, you have the grain boundary acting as a potential barrier. So the density of state is just large when you have the lander-level developed inside the grain, but very weak outside. But when you are in between lander-level, where you would expect to have a plateau of the quantum Hall effect, actually what you see here by projecting, for instance, here for this case, the density of state or in the system, you have state only on the grain boundary, and actually the grain boundary network is providing a pathway for electrons to go out of the system. So actually this is preventing the formation of the localization of states, and so the formation of plateaus in between lander-level. So, but of course, this will have a certain scaling trend, which you could investigate on the experimentally. Finally, I wanted to point out the spin transport in this polycrystalline graphene, because for using this material in Spintronics, we are facing the same question that what is actually the system, the morphology of the system, or it impacts on the upper limit for transferring spin information, for instance. So there have been a few years ago some experimental measurements at IMEC and in the institute, where they could investigate a lot of devices and get a kind of not kind of universal value for the spin diffusion length of 10 micron for the system deposited on top of silicon oxide. But the question was, all grain boundary and all the average grain size can play a role in that. So we developed some simulation with some collaborator in UCL in Belgium. So modeling grain boundaries and polycrystalline graphene is quite complicated, but we eventually found a model that is quite universal. So we could compare with structural defect and by DFT calculation and our model. And at the end, by simulating the transport of the spin, we could end up with a very interesting result, which is that actually the spin diffusion length is independent on the average grain size. It is only driven by the strength of the spin orbit coupling, which is conveyed by the substrate. But the grain size and the grain boundary are actually not appearing explicitly in this spin diffusion length because of a compensation between the scattering and the spin relaxation. So with this kind of simulation, we could make a kind of prediction of a kind of universal spin diffusion length when graphene was on top of silicon oxide, and we reach typical this type of spin orbit coupling strength. We get 10 micron, and for graphene on top of boron nitride, we got some 50 micron. But this is very important because if we want to use polycrystalline graphene for Spintronics, we don't really need to have a system of 5 micron average grain size. If we have 100 nanometers, it will work the same because the upper limit for spin diffusion, for propagating spin information is actually exactly identical. So it shows that you have this grain boundary and this polycrystalline morphology are actually very interesting. They show multiple property, and depending on what you are interested in, you can find a trade-off between the investments you have to do in terms of the growth and the resulting property of the material you are interested in. So I'm finishing with this slide, which is you can find more information about actually more scaling property of polycrystalline graphene. This is a review we wrote several years ago, and we review all the aspects on electronic transport, but we also discuss mechanical property and thermal property, and so a kind of guidebook for engineer or experimentalists to if they kind of to understand what is the material which is able to provide the property of interest for a certain application. So I think I'm done, done with my time. I want to let the question entering in the conversation. I finished with this slide acknowledging all my group members at ICN2, and also I acknowledge all of you for your patience, and I'm looking forward to your question. Thank you very much.